Hello students, today we are going to discuss a very important topic that is called the magnetic field. So the first question comes that what is the magnetic field? In simple words we can say that the space around a magnet within which its effect can be experienced is called a magnetic field. The second question comes that what is the cause of magnetic field? In the very fundamental way we can say it is caused by a charge in motion. So we will discuss this thing in little bit details. Whenever a charge is in motion, it produces a field. That field is called magnetic field. Let us discuss this thing in details. Here we have a circuit through which a steady current is flowing. You must note that I have told steady current. Steady current means the current is not changing with time. So for steady current we have applied the DC battery here. This is the positive terminal, this is the negative terminal, and the current I is passing through this circuit from this direction to this direction. If I put a charge Q here which is stationary, then we will see that no field is acting on this charge. When this charge is stationary, no field acts on this charge. But if I move this charge, experimentally it has been shown that whenever the charge is moving, a field is experienced by this charge, and that field is called magnetic field. So let us see, if charge is moving with velocity v, what type of forces are acting on it. First of all, the force which is experienced by this charge is directly proportional to magnitude of the charge. Then it is directly proportional to the velocity of the charge. And thirdly, it is directly proportional to the sine of angle theta between direction of velocity and direction of magnetic field. If I combine all these things, we will get Fm is proportional to QV sine theta, or Fm is equal to QVB sine theta. So this B is called magnetic field. In vector form we can say, in vector form, this magnetic force Fm is equal to QV cross V. This force is called Lorentz magnetic force. So this magnetic force is a vector quantity whose direction depends upon the direction of velocity v and magnetic field B. The direction can simply be identified using the right hand thumb rule. The right hand thumb rule says that if velocity v is directed along this direction and vector v is directed along this direction, then using the right hand we can curl the finger from velocity to B, and the thumb expresses the direction of magnetic. That is called the direction of magnetic. Simply, the direction of F is always perpendicular to the plane containing both the vectors V and B. Or in simple words, we can say that Fm is perpendicular to velocity vector V as well as Fm is perpendicular to direction of B. Or if two vectors are perpendicular, then their dot product is always 0. So we can say that Fm dot B is 0 and Fm dot B is 0, because dot product says that A dot B is equal to AB cos theta. If theta is 90 degree, then cos 90 will always be 0. This means to say the force Fm is perpendicular to both V and B. So this is all about the direction of force. Now we can find out the SI units of the magnetic field. So here we have the magnitude form of magnetic force. If I keep B on one side and take other quantities on the other side, we can write like this: QV sine theta. Since theta is a dimensionless quantity, from here we can calculate the units: Newton per coulomb per meter second. This is called Newton per coulomb per meter second, which is called Tesla, or it is represented by capital T. So these are the units of magnetic force. Let us come to the other point, that this is the force on a charge moving with velocity v. If more than one charges are collectively moving in a one direction, that is called the current. So come to the second point. The motion of a charged particle in a particular direction constitutes a current. So whenever a current is flowing in a wire, let us say that this is a wire and a current I is passing through this wire, then due to this passage of current, a field is produced around this wire, and that field can be measured using Biot Savart's law. So let us take the small portion of this current of length dl, that is called the current element. This current element can be written as I dl. As we know that current is a scalar quantity, but length dl is a vector quantity, so combined form is called a current element. So the force on this point P due to this current element of length dl is given by Biot Savart law, which is equal to mu naught upon 4 pi I dl cross r upon r cube. Here r is the distance between this current element and the observation point. This is very important result to find out the magnetic field due to a current carrying wire. This is the small magnetic field due to this small portion of the wire. If you want to calculate the magnetic field due to whole wire, you can integrate from initial length to the final length. You can get the final value of magnetic field. From here, it is clear that the direction of B depends upon the direction of dl and vector r. Again, this vector B is perpendicular to the plane containing vector dl and r, and direction of this magnetic field B can again be obtained by using right hand thumb rule. So this is the form of Biot Savart law. If I talk at the atomic level, this is the macroscopic form of the magnetic field. If I talk at the atomic level, the smallest current element is the electron revolving around the nucleus. We will discuss this portion later on, and this portion is very much responsible for the magnetic characteristics of the elements. And due to this portion, we will explain diamagnetic properties, paramagnetic properties, as well as the ferromagnetic properties. So keep in mind that the smallest current in atomic level is the electron revolving around the nucleus.